This is video 3 for the Gravity, Force, and Space Unit. So in this one we're going to talk about the G factor for gravity. Now you'll note that the force of gravity depends on the mass of an object. So a heavier object has a greater force on it. So the question becomes, why do all objects reach the ground at the same time? Since the fact that heavier objects or more massive objects have a greater force pulling on them. And it comes down to the fact that acceleration is force divided by mass. So, larger objects have a greater force pulling them down. But they also have larger masses. So this works together then. Notice that if the force becomes larger and the mass becomes larger, well, the acceleration could potentially stay the same, and that's what happens. So every object will have the same acceleration as they fall. That acceleration, which we label with a G because it's for gravity, is 9.8 meters per second squared, or 32 feet per second squared. So what that means then is if you happen to be falling, your speed will increase, and 32 feet per second squared, that works out to 22 miles per hour every second. So after you've fallen for 1 second, you will be traveling at 22 miles per hour. After 2 seconds, you'll be traveling at 44 miles per hour. And it just keeps increasing. Now that's falling. What about running? So let's say we have a world-class sprinter. They can do the 40-meter dash in 4.4 seconds. So what that does is it works out to an acceleration of 4.1 meters, or 4.1 meters per second, I should say, every second. So, at 0 seconds, they are traveling at 0 meters per second. After 1 second, they are traveling at 4.1 meters per second. After 2 seconds, they're traveling at 8.2. And then after 3 seconds, we can keep going on. 12.3. Yeah, we can keep going. Eventually, once you reach 4.4 seconds, you can calculate then how fast they will be traveling. So we can turn this, we can relate this to the acceleration due to gravity. So if I take 4.1 meters per second squared. Meters per second squared is the same thing as meters per second per second. If I divide that, multiply by 100 to turn it into a percent, that comes out to about 40% g, or 0.4 g's. So that's their acceleration. Not quite 1 g, but 0.4 g. So, what is the speed needed to reach 100 kilometers into the air? And, what's interesting is that we see a lot of symmetry in nature. The speed needed to reach 100 kilometers will be the same speed an object gained after falling 100 kilometers. And that's really handy because we have this nice little model or formula that says height, drop height, equals 1/2 g t squared. So if I were to plug in the parameters here, 100, so I'd have 100,000 meters equals 1/2, g is 9.8, times t squared. You could work out this math. The time would be 142 seconds. So it takes 142 seconds to fall 100,000 meters. Now again, we're ignoring all air resistance in this. Now, an object gains 22 miles per hour for every second that it falls. Again, that's ignoring air resistance. So, if I take 22 miles per hour and multiply that by 142 seconds, what that gives me is 3,124 miles per hour. So, again, ignoring air resistance. What this seems like a really fast speed, but if we do some converting, this is actually about 0.86 miles per second. So it's really not quite as fast as you might think. The next question I might ask is, okay, well, how much more energy does that take? So, kinetic energy is 1/2 mass times velocity squared. So, let's use my mass. I am roughly 90 kilograms. Yeah, that's going to change, I'm sure. But I'm right around 90 kilograms. So, my kinetic energy then 1/2 90 kilograms times that speed, which we need to convert that into meters per second. So this comes out pretty close to 13 meters per second. And that gives me, got to square that, 7,600 joules, which is right around 1.8 calories. Food calories. So really, it doesn't take as much energy as you might think to do that. All right, going on with another similar topic, air resistance. A moving car will feel the force of air on its front. That slows the car down. So in order to keep going at the same velocity, the engine must make up for that lost energy. It's supplying energy to keep it moving. Now, at a speed of 67 miles per hour, the force of air on the front of a car is around 500 pounds. And obviously, that depends on the design of the front of the car. So if we take a look at how cars have changed over the years, what we notice is that they kind of become a little more aerodynamic, a little more streamlined. And that's to, save on air resistance. That way you're not pushing that 500 pounds around. Now at higher velocities, more than half of the gasoline that you burn is being used to overcome air resistance. And it's due to the kinetic energy being 1/2 mv squared. So if we think about it, at half the speed, the force is only a quarter as much. So the vehicle would use a quarter of the gasoline to overcome air resistance. So if you want to have a fuel efficient car, you either need to design it so that it's very aerodynamic so that you don't have as much air force pushing on the front of it, or make it less massive, lower the mass, or just simply drive slower. All right, going back to that G rule we mentioned earlier, we can think of acceleration in terms of G. And it's going to let us solve physics problems in your head. So suppose I told you I'm going to accelerate you in a horizontal direction by 10g. How much force would that take? Oh, well, it would just be simply 10 times your body weight. So that's what this rule is really good at, making very quick approximations. Astronauts are accelerated by 3g during liftoff. So that means that when they're going through liftoff, they feel 3 times heavier than they normally would. So if you weighed 100 pounds, they would feel like they weighed 300 pounds. Now, the way we can kind of derive this, force equals mass times acceleration, and then weight, the force due to gravity, is mass times g. And let me change that to an A. So, force due to gravity is the same thing as a force, so I can set these two equal to each other. We see that the acceleration will be the acceleration due to gravity. So g is an acceleration. And mass, m is for mass, and it's a constant. So F would be your weight. So again, using this G rule, we can do very simple calculations very, very quickly. Okay, going on with some math. If we want to go into orbit, it takes a velocity of 8 kilometers per second. That is the requirement to go into orbit. Now, we use rockets to do that for us. But what if we just took a railgun and just shot the object into space? Use some gunpowder, use some electromagnets, did something just to shoot the object into space. Well, first off, we'd have to know a few things. Let's say that the railgun is 1 kilometer in length. So we have a formula that looks something like this, where the final velocity is v, the initial velocity is v naught, 2, and then the acceleration and the distance. So looking at this, the initial velocity would be 0, the final velocity would be 8 kilometers per second, and we know the length. So the acceleration would equal v squared divided by 2d. And this gives us an acceleration of 32 kilometers per second squared. So that would be 32,000 meters per second squared, which would be 3,200 G, since we can say G is 10. It's 9.8, but we can round it to 10. So looking at that, if we put an astronaut into this railgun, they would feel like they weighed 3,200 times more. So instead of weighing twice as, or 3 times as much, they would weigh 3,000 times as much. So if you weighed 150 pounds, you would weigh 480,000 pounds during takeoff. That is a lot. All right, finally, let's talk about the acceleration during takeoff for just a regular airplane. So the takeoff speed for a commercial plane is 160 miles per hour, which comes out to be about 0.07 kilometers per second. So in the average runway, it's about 1 kilometer. So this gives us an acceleration of something pretty small. It's about 2.45. So this would have a value of 0.245 G. So it's so small that you wouldn't even notice it. All right, that concludes video 3.